Building a massive piece of infrastructure like a sweeping highway interchange or a high-capacity dam carries immense physical and financial stakes. A single oversight in the planning phase can lead to catastrophic failure. For decades, planning meant relying on traditional 2D flat maps. The problem is that a flat map only shows you surface borders. It hides the invisible constraints beneath the surface, like deep soil instability or historical flood zones. When an area has millions of disparate environmental and infrastructural data points overlapping, engineers face a major challenge. How do you synthesize all of those invisible variables into one clear, actionable plan? The solution is a Geographic Information System, or GIS, a dynamic framework built to input, store, manipulate, and analyze geospatial data. By structuring data in this way, GIS allows civil engineers to move away from guessing based on surface appearances and begin making safe, data-driven decisions. For GIS to function, it requires three core components working in tandem: the physical hardware, the operating software, and the data itself. Let's look at how this data is applied in a high-stakes scenario. Imagine we need to select the optimal location to build a new hydroelectric dam in this complex, rugged river valley. The process begins by laying down our first layer of geographic information, grid data, also known as raster data. This format takes the map and divides it into a vast matrix of equally sized cells, or pixels. Grid data is the best format for mapping continuous data, phenomena that change gradually over a space. We use it to create a digital elevation model that maps the shifting terrain of the valley, and we can stack another grid to track annual rainfall intensity. Laying down this continuous raster layer gives engineers a precise mathematical understanding of how the natural environment gradually shifts and behaves. Next, we need to add a completely different type of information: vector data. Instead of pixels, vector data uses exact X and Y coordinates to define sharp points, lines, and polygons. In our dam scenario, vector data is used to map discrete features with clear, hard boundaries. We use polygons to define existing property parcels, lines to map out the highway routes, and points to mark individual buildings. Stacking these visual layers is highly effective, but the real power of GIS comes from the unseen engine running behind the graphics, the Database Management System, or DBMS. The DBMS is where the actual information is stored and manipulated. It securely handles large datasets and allows multiple users to retrieve and update the exact information they need simultaneously. Because the visuals are directly tied to this data engine, engineers can run complex SQL queries. We can literally ask the system to filter the entire map for areas that feature steep slopes and high groundwater potential, and the graphics will instantly highlight only the zones that meet our exact criteria. This connection between spatial graphics and a relational database gives GIS its utility as an interactive problem-solving engine. That layered methodology isn't exclusive to building dams. It forms the analytical backbone for almost every subdiscipline in civil engineering. This slide breaks down those specific applications. Looking at the bottom, geotechnical engineers rely on GIS for soil mapping and assessing slope stability to pinpoint landslide hazards. Moving up the list, water resources management uses the system to analyze entire watersheds and generate floodplain maps for drought and flood mitigation. And at the top, urban planning and development utilizes it to manage land parcel zoning and identify the most suitable locations for new residential or commercial infrastructure. This summary infographic illustrates the sheer scope of the system. Swapping in specific data layers allows engineers to adapt GIS for almost any infrastructural challenge. Back in our river valley, once the layered GIS model of the dam project is fully assembled, the hardest work actually begins. This is the stage where we conduct spatial analysis. This is the process of examining geographic patterns and relating different attribute data together to understand how these physical features actually interact in the real world. This slide of case studies highlights how spatial analysis ultimately gives engineers the power to predict outcomes. The very first point shows how they can evaluate the environmental impact of a proposed dam in a digital space, long before any real-world construction begins. Ultimately, this technology shifts civil engineering away from reactive trial and error toward a proactive science of prediction and mitigation. Mastering this invisible digital architecture is now an essential prerequisite for safely and efficiently building the physical world around us.